Today we will go deeper into atomic and nuclear physics, so this will be lecture number 2. So atomic and nuclear physics, and this will be lecture number 2. And we will go here deeper to the atom structure of the atom, to the nucleus. And as we have discussed previously, quantum mechanics, that when we are dealing with atomic scale phenomena, energy is absorbed or emitted in discrete amounts called quanta, or if we are speaking about energy that is emitted or absorbed as a light, and then we can think light as a wave, or we can think light as a flow of particles, so as photons. So today we will go to the deeper into quantum mechanics. So and we will discuss the nucleus of atom, and so nucleus is the core of the atom, and it contains 99.9% of atomic mass. Atom is the scale about 10 to minus 10 meters. Nucleus is the scale of about 10 to minus 15 meters. And there are three nuclear particles, so protons, two nuclear particles, but three particles that are in the atom. So nucleus, protons, they have positive charge, and abbreviation is P+, and neutrons has no charge, so we have abbreviation as N and 0. And we have around nucleus, we have electrons. So electron, as you know, is E-, because it has negative charge. So nuclear notation is the chemical element that's marked with X, and it has A and Z, A superscript and Z subscript. So A is the number of, this is the number of protons and neutrons. Z is the number of protons, and N is the number of neutrons. So N we don't see here, but A is Z plus n. So here is the number, and number of electrons is usually equal to number of protons if it's not ionized state. So this is protons plus neutrons and protons. This is only protons. And number of electrons usually equal to the number of protons because of charge balance. And this is the sum of neutrons plus protons. If we subtract from A minus Z would be equal to number of neutrons according to this. Yes, neutrons and protons and protons, and some elements they may have the same number of protons, but they may have the same chemical element may have the same number of protons but different number of neutrons. So like so it means that this Z number will be the same but A number will be different, like uranium isotopes. There is U235 and 92 here, and U238 92 here, or hydrogen isotopes can be H11, can be H21, can be H31. So this is called protium, deuterium, and tritium. As you see, they have one proton each, but this one doesn't have neutrons, because this is the sum of protons and neutrons. If there's one proton here, it stands for proton. This has, so 1 minus 1 would be 0 neutrons. Here neutrons would be 2 minus 1 would be 1. Here 3 minus 1 would be 2 neutrons. And because there are protons have positive charge. So this positive charge is concentrated into so small volume. So protons and neutrons, and this is around electrons orbiting, like electron cloud we can imagine, but for simplicity here. So because we have protons here, and this is repulsive force, they are pushing each other to sides, so that means that some kind of force has to be between them. So there is nuclear force, there is binding force. So nuclear force is attractive force, and holds the nucleus together, and does not the force it's how do you say, it's field of this force, where this force is active or where it works, let's say in simple words, does not extend beyond nucleus. And this force is between attractive force between neutron and neutron, between neutron and proton, sorry, and between two protons. So this is attractive force. And as you know, as you if you look at the table of the elements, chemical table of the elements, you would see that when elements have so once again, let's go back to this. This is called A. This is called atomic. Sorry, A is called atomic mass. This one, atomic mass. This A thing. Z is called atomic number. Atomic number, and this is neutron number. Because protons and neutrons, they together make 99% of the atom mass. So this is called mass numbers. Protons and neutrons they are responsible for mass. So when the mass increases, or when the if for elements that are heavier elements, which have I don't have the chemical, or maybe I have somewhere around here. So for the elements that you can see, this is a table of elements. You can see for the elements, this is in Lithuanian, but nevertheless, but you will see that. Let's look here. Let's look at here at the calcium. Calcium has 20 protons and 40 and atomic mass number is 40, so it means 20 protons plus 20 neutrons. So you see that protons and neutrons number is the same, but then when we go further, we can see that platinum it has 78 protons and 195 neutrons. You see what happens here. We go to radium. Radium has 88 protons and 226 88 protons and 226 neutrons plus protons. So the number of this is the sum of protons and neutrons. So in platinum it was 195 protons and neutrons. In radium it is 226 protons and neutrons, and you can see that when the mass increases of a chemical element, it means that the number of protons increases, but the number of neutrons that it has increases drastically. Why? Because when there are more protons here with plus charge, so that forces that they are pushing each other far away, it becomes so that force becomes so large that it needs more and more neutrons to hold them together, because neutrons provide nuclear force, not electrostatic force, not electric forces. Negative charge would provide, but they provide only this nuclear force, as neutron holds together these protons also in this case. So for the nucleus to be stable, they provide this nuclear force. And as you see here, radium, it is 88,226, and all these elements, you see, it means this is radioactive science, radioactive. So it means that these are unstable. So it means that even though they have a lot of neutrons, but they are still unstable. So they are radioactive. It means that if they are radioactive, they have unstable nucleus, and it means that they decay to smaller nuclei. So elements, so the role of neutrons hold or bind the atom. What is the better English word? So they just hold the atom nucleus, better to say nucleus, particles in nucleus together. So neutrons, so they are like glue. They hold, bind, or glue particles in nucleus together. So that's what they do. It is their function. So, but even though atoms, chemical elements, atoms of the chemical elements who have a lot of protons and even more neutrons, they are radioactive. So elements which have very high mass number, so are unstable. They are radioactive. It means that they have unstable nuclei, which how to better describe, which undergoes splitting reaction, physical reaction. This would be physical reaction to nuclei of more stable elements. And in this process, radioactive particles or waves are emitted. So it's generalized principle or theory. So during radioactive decay, so three kind of particles, we can say particles, three kind of radioactive particles can be emitted. So this is called alpha particles. Alpha particles. This is the alpha particles, so they are written like alpha, and this is alpha particle is nucleus of helium gas, nucleus of helium gas. It has doesn't have electrons, has 2 protons and 4 minus 2 neutrons, and doesn't have electrons. Then it is beta particles or beta rays, and this is electron. As you know, electron can be thought as a particle or as a wave, so particles or rays. And then gamma rays, and gamma rays, they are simply photons. Photons of very short wavelength, very energetic. Because these particles have different charge, so this has plus charge, this minus, this has no charge, so they act differently in magnetic field. So in magnetic field, as you remember from electromagnetism lectures, so when in external magnetic field, particles, they go positive and negative particles go to different directions, and photons directions, they don't change. You can go back to this lecture of how particles act in this magnetic field and just review this, because it will be useful for exam. And the direction of photons isn't changed. A device Geiger counter, Geiger counter, maybe Geiger, it will be pronunciation, counter, detects the presence of radioactivity. It works like alpha, beta, or gamma rays. They ionize the gas, and this produces electric current, which is monitored by this device. So according to the level of the danger, so all these are dangerous, and extreme caution has to be taken if you're working with them. Or alpha particles can be alpha particles are the least dangerous of all these. Beta are more dangerous, and gamma rays are the most dangerous. Alpha particles can be these are heavy particles, electrons, heavy particles. This means that they don't have this. So they are, due to this, are less dangerous. So electrons are much lighter than these, and photons are the lightest. So and they can penetrate. Gamma rays have short wavelengths, have high energy, and because they are photons, they have Photon has basically no mass. What is interesting, not only gamma, but everything according to Einstein, so photons can penetrate through very very thick metals and it's very hard to protect against these rays. Although against these it's possible. So half-life of radioactive substance of some kind of element. So half-life is written like this: T, it is time, necessary for 1/2 of radioactive of a sample of radioactive substance to decay. So it is time. We cannot predict when particular nucleus will decay, but we can predict on average the behavior of population of the nucleus. Say if we have 1,000 atoms, so we can say that 500 nuclei will decay, let's say, in if T is 2 years, so we can say that after 2 years 500 of these radioactive nuclei will have decayed. Okay, now nuclear reactions. So when nuclei decay, the nucleus of initial element, it is transformed to another element's nucleus. And for example, if we have alpha decay, so example would be we have radon maybe radon. It is 22286, and it splits to polonium and 2 and helium nucleus is produced. It has charge plus T, so it means that 2 electrons are also produced here, but these electrons are not because of they just leave this helium atom and they just not because of it is not beta decay, it is just alpha decay. So we can see that here we had 222 and 86, and here we have 218 and 4, so it means that would be 222 if we sum, and 84 plus 2 would be 86. So it is this is alpha particle. Beta decay. In beta decay, 1 neutron splits into, decays into 1 proton plus 1 electron. So example of this would be carbon, radioactive carbon 16,6. It decays into 16. It decays into nitrogen plus electron, because one neutron has decayed into proton and electron, so it means that one neutron from here decayed to proton. So proton number here is 17, but because neutron decayed to proton, this number is the same, but electron is produced. And gamma decay. During gamma decay, excited nucleus of, let's say, carbon 12-6, it decays into carbon which nucleus is stable, plus gamma rays. These are photons. So you see there were no changes in protons or neutrons. So this carbon applications of speaking about carbon is carbon dating. It is that according to the radioactivity of carbon, scientists can, because they know the half-life, they can predict the age of organism. And another thing is that in medicine, cancer treatment, because when these nuclei produce, radioactive nuclei produce alpha, beta, or gamma radiation, these nuclei can be embedded in tumors, and when they produce this radiation, they damage or simply kill cancer cells, and this is the form of therapy. Another application is nuclear energy, as you know. Nuclear energy, because there is enormous amount of energy in the nucleus, so it can be used in nuclear reactor, or it can be used in nuclear bomb. In nuclear reactor, the energy is controlled. In nuclear bomb, the energy is uncontrolled. So these are the simply applications. And now speaking about radiation. So radiation, alpha, beta, gamma radiation, it is harmful because they can ionize molecules in cells and turn cells to cancerous cells. So they are cancerogenic because they damage DNA. So due to DNA damage, so because they damage these things, they damage DNA and turn cells to cancerous. And depending on the dose, people may get radiation sickness if the dose is not very if it's not that high, they get radiation sickness. If it's very high, they can get death with severe symptoms and leading to death in days to 1 or 2 weeks. And radiation sickness, they get vomiting, nausea, burning, bleeding, they get cancer, and that's it if the radiation dose is not very high. But if it's very high dose, lethal dose, so then there are severe symptoms and the person dies in a few days. So energy from the nucleus, energy, speaking about energy, let's go out from bad things. Speaking about energy from the nucleus, can be obtained in two ways. Nuclear fusion and nuclear fission. So in nuclear fission, a heavy nucleus splits into lighter nuclei. Let's say one heavy nucleus splits into two lighter nuclei by emitting radiation. And in nuclear fusion, two lighter nuclei fuse to make one heavy nucleus. Let's begin with nuclear fission. So nuclear fission, we have, let's say, we have example uranium. We have the nucleus of uranium 23592, and in order to induce the nuclear reaction, it has to be hit by neutron. So one neutron hits uranium nucleus, and this nucleus is then splitting. So it is 23692, so it has absorbed this neutron. This nucleus absorbed this neutron, and it splits to two. So it splits to, one is krypton 9236, another one is barium 14156, and also there is 3 neutrons generated, and the energy that is generated by nuclear fission is in kinetic energy of these two. Mostly it is the most it is released in the form of kinetic energy of these 3 neutrons, so they move in very high speeds. So EK of these neutrons is the energy from nuclear fission, kinetic energy released in neutrons. Now nuclear fusion. Nuclear fusion, two lighter nuclei, they collide. They have to collide at very high speeds. So this is hydrogen deuterium. It collides at very high speed with tritium, and what we get is we get hydrogen, which has 2 protons and 2 neutrons, so it means that 1 neutron is lost, and during nuclear fusion, you can predict that the energy is released in the form of this of kinetic energy of this neutron. And nuclear fusion is the energy source for all stars, but for this, these have to collide at very high speed. And nuclear reaction releases 10 times more energy than any chemical reaction, 10 million times more energy than chemical reactions. And this energy is because it comes from famous Einstein theory. E is mc squared. So this is Einstein's theory of special relativity. This is not the theory, but this is the one result of that theory that was derived by Einstein, so that mass can turn to energy and energy can turn to mass. So mass, if you have plutonium and plutonium is excited, hit by neutron, it collides with neutron, and we get strontium, we get barium plus neutron. So mass here is 240.06 mass units, and here we get mass 239.86 units. So you see that reactants have more mass than the products a bit, and this very small, we would say insignificant change in mass gives a lot of energy, because mass is multiplied by c squared. Very small, and c squared is 3 times to the 8 meters per second, so squared it would be times to 16. So this small change in mass, insignificant to our everyday lives, insignificant change in mass produces very high energy in atomic scale. Okay, so the next thing is these nuclear reactions. It's very important that nuclear reactions occurs in chains. Nuclear reactions occurs in chains. So this is the key to release large amounts of energy. So if we have uranium-235 and we hit it with proton, so it collides with proton, and we may write plus here. And what happens? It happens that thing that we have here, krypton 9436, we have barium 13956, and we have also 3 neutrons. And these 3 neutrons, they hit another uranium-235 92, 235 92, 235 92. They hit another uranium, and what happens again? We get krypton, we get barium, we get krypton, we get barium, we get krypton, we get barium, and here we have 3 neutrons, here we have 3 neutrons, here we have 3 neutrons, and these 3 neutrons can strike again. They can strike another uranium, so maybe we can draw like this: 3n, 3n, 3n. So these 3n can strike again. And as you can see, this reaction, it goes like chain, it amplifies itself. So if this reaction is controlled, then we have nuclear reactor. In nuclear reactor, fission is used, and for nuclear in nuclear reactor so in nuclear reactor nuclear power plant, nuclear fission occurs. Fuel is uranium-235 or plutonium-239. Fuel is assembled in rods, and the obtained heat turns the power turbine. So it's the same as something as other power plants. Just here, heat obtained from nuclear reaction turns the turbine. Nuclear reactor, nuclear bomb. Nuclear bomb, it utilizes uranium-235, and there also fission occurs, but in this it is controlled in nuclear reactor, in nuclear bomb uncontrolled. So they both work on fission. Now nuclear fusion. Nuclear fusion is held as here we were talking about nuclear fission in nuclear reactor and a nuclear bomb, and nuclear fusion is held like energy source of the future. So sorry, I made one mistake. I made one mistake where I was writing here. You see, it's not hydrogen. Sorry, it's helium. Helium had to be here. Nuclear fusion. Okay, it's good that I remembered, because I was speaking about hydrogen. I just said hydrogen and wrote hydrogen 42. So sorry. So this has to be helium. See, go back to this to this part where we were speaking about fission and fusion. Okay, so nuclear fusion, we had hydrogen 2-1, we had hydrogen 3-1, and they collide at very high velocities, produce helium plus 1 neutron. And also it is used in hydrogen bomb, this fusion, and kinetic energy is released in the form of this neutron. So energy released as kinetic energy of this neutron, and but for this, these have to collide at very high velocity. So in order to gain this kind of velocities, the temperature is needed compared to the sun's. So in order to make controlled thermonuclear fusion and create power plants for the future, it is very high temperatures are necessary. This is the main thing that is stopping from these power plants from being created and being efficient. And the way out from this is that magnetic fields can be used instead of vessels for very high temperature, for hydrogen gas that are in very high temperatures, because from these very high temperatures the vessels will burn. So instead of vessels, magnetic fields can be used. And now collaborative projects are being done between countries around the world to make this possible and to make this future power source, because this is clean energy, has no greenhouse gas emissions, practically no waste, and there is no danger of nuclear disasters either. So this was the lecture about nuclear fission and fusion, about radioactivity, and this was the last lecture, and thank you for listening.